Good evening, students. In this session, we are going to look into the concept of symmetric and skew symmetric matrices. So, already you are familiar with the concept of transpose. So, we'll look into one by one symmetric matrix, what it is. I'll give a simple definition. There are two ways of understanding what is a symmetric matrix. If the transpose of a matrix is equal to the original matrix. We have learned transpose in our previous class. That is, you take the matrix and convert rows to columns and vice versa. What happens is you get the transpose, compare it with the original matrix. If they happen to be same, we call such a matrix. So then A is a symmetric matrix. Let me give immediately an example for this one. But when I introduce the symmetric matrix, and when you are doing the transpose, there is a difficulty here. When you are interested in doing transpose, I told you the order does not matter. But when we are discussing the concept of symmetric, the order definitely matters. The transpose of a matrix, when you take, make sure that the matrix given is a square matrix. So unless the matrix is a square matrix, we will not be able to come up with an exact symmetric matrix. So unless the orders of the transposed matrix and the original matrix, the equation, the matrix on left, matrix on the right already conveys that meaning. Two matrices cannot be equal if their orders are different, isn't it? So therefore, for this equation to be fulfilled, for this to happen, the essential condition is this has to be a square matrix. So let me put it as an essential condition. A has to be a square matrix. Or else, if that is not true, then A transpose will have a different order than A. Alright, so let us go for example 1. Let me give a simple 2 by 2 again. I am writing the diagonal elements and I am writing some other, I am filling the matrix, whatever it is. Now take the transpose. So if you take the transpose, what happens? The row 1 becomes column 1. The row 2 is written as column 2. But you find no change between A transpose and A matrix. So let us go for another example, a 3 by 3. Where let me write the diagonal elements and then let me say this is how it is written. So let us put it like this. The matrix B has 3, 2, 4 in row 1, 2, 5, minus 1 in row 2, 4, minus 1, 7 in row 3. Let us go for the transpose of the same matrix. Students can immediately write the answer. Row 1 takes the position of column 1, row 2 takes the position of column 2, and row 3 written as column 3. But what do you find? There is absolutely no change in B transpose and B. They are very much same. Element by element you can check. There is no change in the location of the elements. All elements are exactly in their original position even after you transposed. How does this happen? Is this happening by magic? Well, I formed the matrix. A few students could have noticed what I was doing when I wrote the matrix. What was I doing? I was writing the diagonal elements first and then filling the elements in the rest of the positions. But then I ensured that I am writing the same 2 in 2 places. Did you not notice? Did you also not notice I am writing 4 in 2 places? The same way I was writing -1 in 2 places. So why is it so? So let us now look into the alternative definition of the symmetric matrix. So the symmetric matrix can also be defined like this. Okay. If Aij is same as Aji, the element in ith row jth column happens to be same as jth row ith column, then such a matrix is symmetric. It implies symmetric matrix A. Alright. So it is not happening by coincidence, it is planned such a way that the element occupying Aij, for example, take the address A12, first row second column. Now you invert the address Ij, invert it as Ji, which means A12 referred to turned to A21. You will find A21 means second row first column, so you can find the second row first column also has the same number, the same entry as in row 1 column 2. Alright, so the same thing you can refer with every singular element. That is why after transposing you don't find any change occurring in the given matrix. Transpose matrix remains the same as given matrix. So that is your symmetric matrix. Remember, the matrix has to be a square matrix. That is the essential precondition. Let us go into the next skew symmetric matrix. So once again I can give you 2 varieties of explanation, 2 varieties of definition for this matrix. How does that happen? The very first one, let us say, let me give you the technical explanation. After transposing, you find it is negative of the given matrix. You transpose, there was a matrix given to you, and once again remember that it has to be a square matrix, not otherwise, okay, and you happen to take the transpose. After taking the transpose, you find it is the negative of the given matrix, which means every entry element in A, the sign has been reversed. Okay, so how is that? Let me give you example 1. Let me take a 2 by 2 matrix. Consider the matrix A. So the given matrix I am assuming as 0, 2 in row 1, -2, 0 in row 2. Can you write the A transpose now? What is that? 0, 2 in row 1, -2, 0. I have not transposed, so I am writing the transpose of that, okay, which means 0, 2 in column 1, -2, 0 in column 2. So that is what is happening. Now I can find between the given matrix A, don't you find the sign is changed? 0 remains 0 because the sign inverse, sign reversing does not affect it, but the positive 2 from given matrix has become -2 in second row. -2 has become +2, which means I can write this as negative of 0, 2, -2, 0, which was the given matrix. So this is the fact about skew symmetric matrix. Let us look into another example, which is 3 by 3 in nature. 3 by 3. Okay, 0, 0, 0 are the diagonal elements. Okay, after filling the elements, the matrix becomes 0, 5, minus 1 in row 1, minus 5, 0, minus 2 in row 2, 1, 2, 0 in row 3. And consider what happens when I do the transpose. So the row 1 written as column 1, row 2 written as column 2, and the 1, 2, 0 of row 3 now is column 3, 1, 2, 0. What has happened? Compare the given matrix and the transposed matrix. 5 got changed, the sign got reversed. Minus 1, sign has been reversed. Minus 5, now it is 5, sign is reversed. So, in other words, I can write B transpose is negative of B. So, that gives you the understanding. B is a skew symmetric matrix. Skew symmetric matrix. Well, once again, how does this happen? This does not happen by coincidence. It is a pre-planned phenomenon. What happened actually when I was forming the matrix, you could have observed that intentionally I wrote zeros in diagonal elements. In diagonal positions I have written zeros only, and I have written the A, for example 1, 2. When I filled the A21 position, what I did, I have filled it with negative of that entry in A12. The entry in A12 is positive 5. The entry at A21 position is negative 5. This is how I have done, and it is pre-planned. Okay. So what can be the alternative definition for skew symmetric matrix? So another alternative I can say, I am representing skew symmetric as like this, SK, SYM. Okay. So what happens is, if every entry AJI means the entries in the transposed matrix, they happen to be negative of the elements in the original position Ij. So it is minus of Ij. So AJI is minus of Aij. Then we can say that the matrix B is A matrix is a skew symmetric matrix. Well, there is a what we call conceptual question very often occurring in CBSE. Why should the diagonal elements be always zeros? In the first example also you observe, I made the diagonal elements as zeros. In the 3 by 3 matrix also I made the diagonal elements zeros. Why is it so? Can there not be any other number? Okay. So let us take it as a question. It's a very popular short answer question. Take it down. Prove that the diagonal elements give a skew symmetric matrix, okay, or zeros. I have written the question like this: prove that the diagonal elements in a skew symmetric matrix are zeros. Well, we know very well, go for the alternative definition. AJI is equal to negative of AIJ. And students are very familiar. How do you write the address of diagonal element? Diagonal in a square matrix, position 1 1, position 2 2, position 3 3 or 4 4, they represent the diagonal elements, which means I can say in with the row column A I. Okay, I am not going for 1 1 2 2 like that. I want to make a generalized notation for diagonal element. So how do I do it? A I. This represents a diagonal element. Fine. And by definition, we know in a skew symmetric matrix, what should happen? A Ji is equal to negative of A Ij. I have written only the definition. That definition applies for diagonal elements also, which means A I same as negative of A I. You can find A negative A they are like terms. I can combine them. So let me transpose negative A to LHS. So once I shift it to LHS, what happens? I get A plus again A RHS empty now, 0. I am adding like terms. 2 times of A is 0. So twice A When I say A students can replace that symbol A with the word in your mind, the diagonal element. So 2 times the diagonal element is 0, which means the diagonal element A should be 0. So you can say, hence proved that all diagonal elements are zeros in a skew symmetric matrix. For simplicity, I have given you some short form SKSYM, skew symmetric matrix. So that is done, students. So we have introduced the symmetric, skew symmetric, and I want students to remember they are all essentially square matrices. Whether we understand it is a symmetric or skew symmetric, they must be definitely a square matrix. Okay, so we'll stop here, and in the next video I am going to go ahead with another some kind of operations in combining the skew symmetric and symmetric matrices. Thank you.